Good day, grade 11s. Today we're going to be looking at a continuation of acids and bases. In particular, we're going to be looking at conjugate acid-base pairs. We're going to be looking at amphilites. We'll be looking at different types of acids, as well as the pH scale. Okay. So if you have not seen the first video, I've sent the link. I've actually dropped the link to the first video in the comment section, and you can go check it out just before you watch this video, because that one was just an introduction. Okay, so today we're looking at conjugate acid-base pairs. So what exactly are conjugate acid-base pairs? So conjugate acid-base pairs, by definition, are pairs that conjugate acid-base pairs are pairs of molecules, or certain pairs of molecules or ions, right, that differ by a proton. Right? So that we say that conjugate acid-base pairs are pairs of molecules or ions that differ by a single proton, right? Yeah. So we say by definition, a conjugate acid, right? A conjugate acid is known to be a certain species. It is a species that actually donates a proton. Remember, an acid, by definition of the Lowry-Bronsted model, is the Lowry-Bronsted theory, is a proton donor. So a conjugate acid is a species that donates, not donated, that donates what? A proton, H plus. So that it becomes its conjugate base. Okay, so said that a conjugate acid is a species that donates a proton, so that it becomes its conjugate base, right? Similarly, if you talk about a conjugate base, right? So a conjugate base, I'm sure you can guess it, a conjugate base. So when you talk about a conjugate base, we're talking about a species, right? It is a species that accepts, right? It accepts a proton. So that it becomes its conjugate acid. Okay, right. So a typical example of this, let's say we have a reaction of hydrochloric acid, right? So say we're reacting hydrochloric acid with water, right? Now what we form? Now remember, hydrochloric acid donates a proton, so we're expecting it to donate a proton to the water molecule. So we have a proton being donated, right? And what do we result in? We then end up with Cl minus plus H3O plus. Cool. So we have HCl reacting with water to give us Cl minus plus H3O plus. And we do know that in this particular case, just a different color, I think blue is gonna green just work just fine. This particular case, this guy right here is our acid, right? And in this case, water becomes our base. But if I had to reverse the reaction, so take a look at something. If I had to reverse the reaction, right? Remember, this is a reversible reaction because of this guy right here, right? So if I had to rewrite the reaction in reverse and have something like this. So if I were to say I have Cl minus plus H3O to give me exactly my HCl plus water. What actually happened? We then see that, okay, if that is the case, then that means this guy right here gave a proton to Cl minus, right? And then it gave you HCl and water. So in this particular case, what can you think of? What can you actually see this as? So you look at this and you're like, okay, cool. So if I reverse the reaction, Cl minus gets a proton and becomes HCl. So in this case precisely, this guy right here acts as a base, right? And he acts as an acid, right? Because it gives away the proton. Similar in this case. So this is basically, this guy here is basically the same as this. So this guy, remember we said is our what? Our base. And then this guy is our acid. Okay, just going to remove this. Just hope you guys are seeing this thing here. Okay, so look at this. Look at this. Now, we say that something is a conjugate. We say that two species are conjugate acid-base pairs. Why? Because if I have my HCl and my Cl minus, right? So you'd notice that my Cl minus is an ion formed from HCl when it loses a proton. So this guy and this guy right here are what we call conjugate acid-base pairs, right? In this particular case, we say that Cl minus is not just a base. We use a proper term and we refer to Cl minus as a conjugate base. It is a conjugate base, right? So Cl minus is a conjugate base. Just going to bring this a bit down because now I just realized that I want to do something real quickly. Okay, so Cl minus is a conjugate base. I think, I'm not sure if anyone can see this. So say that Cl minus is a conjugate base. So Cl minus is a conjugate base of the acid HCl. Similarly, H2O and H3O plus are also conjugate acid-base pairs. Conjugate, in short, you might actually see probably in the textbooks that you guys use at school, they would say this is a conjugate pair, basically. So both of these are conjugate pairs. So the proper term for H3O plus in this case is not just an acid, right? But it's a conjugate acid. Conjugate acid. So what did we have? So we had initially HCl reacting with water, and that gave us Cl minus and a hydronium ion, right? And then we've identified something. If I had to reverse the reaction, right, I would then have Cl minus plus the hydronium ion forming HCl and water, right? So when I reverse the reaction, Cl minus, right, when I read this thing from right to left, right? So if I had to read this, from right to left, then, so if I had to read it from right to left, then Cl minus is expected to what? Cl minus is then expected to receive a proton. When I read it from right to left, when I start reading it from my products to my reactants, I then identify Cl minus as my proton receiver. That means Cl minus in this particular case is a base, but not just any base, but a conjugate base. When I read it from right to left, Cl minus is a conjugate base because it gets a proton, remember? And then H3O plus is a conjugate acid because it donates a proton, right? But if I had to read this from left to right, if I had to read it from left to right, then you would see that HCl gives a proton to water. In this case, HCl is our acid. And then what happens? Water accepts that particular proton, and then it becomes our base, right? So we have acid right here, HCl, with Cl minus. These are conjugate pairs. Similarly, I have water along with H3O being a conjugate pair, right? So in essence, you can think of it in this way. As an acid actually forms a conjugate base when it donates a proton, right? So in simple terms, an acid, in this particular case, what was our acid? HCl. So an acid forms a conjugate base when it donates a proton. When an acid donates a proton, it forms a conjugate base. When a base donates a proton, when a base receives a proton, it creates a conjugate acid. I'll repeat this one more time. An acid forms a conjugate base when it donates a proton. Similarly, a base forms a conjugate acid when it accepts a proton. Okay. I hope that we are all on the same page. I know this is quite a mess. Just a lot going on in this section right here. Okay. So let's just take a couple of more examples. So consider nitric acid, right? HNO3. So let's say we have nitric acid, right? And I react nitric acid with water, right? So it's nitric acid and water. What then happens? Nitric acid and water forms. What does nitric acid and water form? Nitric acid and water will then form NO3 minus, right? Remember from the first video, we see that we only have one H, therefore we can only donate one H. And immediately when I have a minus sign right there, sorry, just erase that. When I have my minus sign right there, that just means I've lost one proton. Okay. Okay, cool. Now, if I look at these and I'm like, okay, so it's nitric acid reacting with water to give me a nitrate ion, right? So it gives me a nitrate ion. Just gonna bring this down there. So it gives me a nitrate ion with a nitrate ion plus a hydronium ion, right? So we have nitric acid. What actually happened? So nitric acid, remember, an acid forms a conjugate base when it donates a proton, and a base forms a conjugate acid when it accepts a proton. So our acid in this case is nitric acid, this guy right here, and he donates a proton, right? What are we expecting nitric acid to form? Since nitric acid donated a proton, we are expecting it to form a conjugate base. In this particular case, our conjugate base will then be the nitrate ion, conjugate base. So the nitrate ion becomes our conjugate base, right? But in this case, HNO3 was our acid. What does this make? The water molecule. The water molecule then becomes our base, right? So it's an acid donating a proton to a base. What does that acid form? A conjugate base, right? And then it's a base accepting a proton. What does that particular base form? That base will then form this guy right here, which is what? Our conjugate acid. Conjugate acid. Right. Right there. So what happens? So if, like I said, similar to the first example, if I had to reverse the reaction, I would then see that H3O plus would then give a proton to the nitrate ion, right? So what happens? So the H2O plus, when I reverse the reaction, when I read it from right to left, then the H3O plus gives a proton to the nitrate ion, right? So what did the H3O plus act as? The H3O plus acted as an acid, right? So we can't have two acids. We can't have an acid on the product side and an acid on the reactant side. That's why we need to have an acid on the reactant side and a conjugate acid on the product side. So we have H3O plus in the product side acting as an acid. That's why we call it a conjugate acid, right? And then the nitrate ion on the product side accepts a proton. Therefore, we say it's a conjugate base. But on the reactant side, the nitric acid, what does it do? It donates a proton to the water molecule. And what does it then form? It then forms a nitrate ion plus a hydronium ion. So in the reactant side, HNO3 acted as an acid and H2O acted as a base, right? Hope we're all seeing the fun of this topic, right? And I really hope I'm making sense. Okay. So what have we looked at? We've looked at conjugate acid-base pairs. We've looked at how it actually works, what conjugate acid-base pairs are, what conjugate acid is, what a conjugate base is, and okay, let's take a different example. Let's take a base. I've just noticed that I've been using an acid so many times. So let's use a base, right? Let's say I have a base. Just think of a base right now. Let's say I have acetic acid, right? HCH3COOH. Sorry, that's an acid. I wanted a base. I'm so sorry. Okay, I'm just thinking of a base right now. Okay. Most common. Boring. So let's say I have NH3, right? And I react NH3 with water. And then what does it actually form? So NH3 reacting with water, then will then form an ammonium ion plus OH minus. Right. So what happened in this case? Now look at this. Look at this. Look at this. In this case, NH3 was a base, right? So it acted as a base, and H2O acted as an acid. Why? Because H2O gave a proton to NH3, right? So what are we expecting to have NH4 as? NH4 plus. Now, yes, you've got it. NH4 plus would then be our conjugate acid. Remember, from the definition, let's just quickly go to the definition. We say that a conjugate base is a species that accepts a proton, right? So we have, in this particular case, the conjugate base is NH4, right? And what does NH4 do? So if I had to reverse the reaction, you would realize that NH4 would then give a proton to OH minus, right? Because there's no such thing as NH5 2 plus. I'm really sure you guys probably never seen this before. So what happens? So NH3, when I reverse the reaction, when I read it from right to left, NH3 gives a proton to the water molecule and to the OH minus ion, and then what then forms? Water and ammonia, right? So in this case, NH4 acted as an acid and gave this guy a proton. So what does this guy in this case? The hydroxide ion in this particular case was a conjugate base. Cool. So what have we seen now? We have then seen that NH3 and NH4 plus are what we call conjugate pairs, acid-base pairs, if you like. All right. Similarly, water and the hydroxide ion also form a conjugate pair. Okay, so that's conjugate acid-base pairs in a nutshell, right? It's very important that you actually understand how this actually works and not just look at this thing like the way it is right now and just grasp now and forget about it later. So it's very important that you understand what goes on here, what a conjugate base is, what a conjugate acid is, how do I identify a conjugate pair, right? Because if you had a question in the exam and they were to ask you identify a conjugate acid base pair, right? So you could have NH3 with NH4 plus, or you're going to have the water with the OH minus, right? So what do you then notice? You notice that NH3 was my base, NH4 was my conjugate acid. So we have our conjugate acid base pair. So we have our, notice, so we have, been using the same colors. So we have our conjugate acid base pair, right? And then with this one just below, the water and the hydronium ions, the hydroxide ions, sorry, I always just mispronounce that, right? So we're going to have the water in this case was our acid. And what is our hydroxide ion? It was our base, right? So what do we have? Sorry, not just a base, but our conjugate base, conjugate base, right? So we have our acid and our conjugate base. So we have our conjugate acid base pair or conjugate base acid pair. I've never heard of that, but it's a conjugate acid base pair, right? So we have our pair, right? So it is very important that you actually understand what actually goes on here, because it's not really a very daunting part of acids and bases. It's, if you can understand the fundamental basics, then trust me, you are going to be fine for the exams. Okay, what do we then look at now? We then look at what we call ampholites, right? Ampholites. Or some can say it is, we say that a substance is amphiprotic. Sure about the spelling, but it should be correct. I don't know. Okay, so we're talking about ampholites, and what exactly is an ampholite? So by definition, an ampholite is a substance, right? It is a substance that can act as both an acid. Oh, terrible handwriting. So it can act as both an acid and a base. So we say that an ampholite is a substance that can act as both an acid and a base, right? So we have different types of examples of of ampholites. The word conjugate is just stuck in my mouth. Okay, so we have ampholite examples. So we look at typical examples. We would have the first one, the most common, is H2O, right? So think about it. So what happens when H2O, remember, I say an ampholite is a substance that can act as a base and in an acid. So let's say water acts as an acid in a certain reaction. What happens? If water acts as an acid, remember, what is an acid? A proton donor, right? So if it acts as an acid, and then it acts as a base, right? So what happens when water acts as just bring this down. What happens when water acts as an acid? If water acts as an acid, we all know that it gives away a proton, right? Therefore, it forms OH minus. When water acts as an acid, then it forms OH minus, right? What is an acid? It's a guy, it's this particular guy that just is so kind and decides to donate his proton, right? What then happens? So when H2O acts as an acid, it forms OH minus. What happens when H2O acts as a base? When H2O acts as a base, it forms a hydronium ion. Yes, it forms a hydronium ion. Great. So this is how it actually works. So when water acts as a base, it forms a hydronium ion. When water acts as an acid, it forms a hydroxide ion. Right? Cool. Then our next example is this one. Also very common, HSO4 minus. So remember from the first video, we looked at HSO4 minus and we said H2SO4 is a conjugate, sorry, why is conjugate in my mouth? But H2SO4 is a, what did we say H2SO4 was? A diprotic acid, yes. Cool. So what happens when H2SO4 acts as a base? So when H2SO4 acts as an acid and when H2SO4 acts as a base. When H2SO4 acts as an acid, so think about it. Let's say it reacts with, so not H2SO4, HSO4 minus. Let's say HSO4 minus reacts with a Cl minus ion, right? So what are we expecting to see? Right, so if this happens, what happens? So if it reacts with that, what are we expecting to get? We're then expecting to get something like this. SO4 2 minus plus HCl, right? So in this particular case, the H2SO4 gave a proton to the Cl minus. Therefore, it acted as a base. So what happens when H2SO4 acts, sorry, it acted as an acid. What happens when HSO4 acts as an acid? It forms SO4 2 minus. So that's what it does here. It forms exactly SO4 2 minus, right? But let's take a different example. Let's say it acts as a base this time around. So what do you know as a base? A base is a proton acceptor. So when it acts as a base, so you'd have HSO4 minus reacting with water, and then what would you then get? You would then get H2SO4. Just bring this to the side. So you would get H2SO4 plus a hydronium ion, right? So when it acts as a base, you get H2SO4 plus a hydronium ion. So here's HSO4 minus. What did it do? It got a proton, right? And then it formed H2SO4. So that's your answer. What happens when HSO4 becomes a base? Acts as a base, it gives you H2SO4, right? And another thing, just something out of this lesson, just a very fun fact. Usually, you'd notice when you get to grade 12, when you're dealing with acids and bases in grade 12, we say that something is a base if it produces OH minus ions, right? Makes sense. Even in grade 11, you know the definition of a base, according to the Arrhenius theory, right? It's a substance that forms hydroxide ions when dissolved in water. So in this particular case, I have HSO4 minus, and I dissolve it in water, and what did it form? OH minus. Therefore, this could be regarded as a base. You guys see what I'm actually talking about? So HSO4 minus, in this case, got a proton, right? It's a base. It received a proton, and it formed as a product OH minus. What do we call something like that? According to the Arrhenius theory, we say that it is an Arrhenius base, right? So HSO4 minus, when it acts as a base, it forms this guy right here, as well as my hydroxide ion. Cool. Is there another example of oh yes. Okay. We then talk about another example of an amphilite. So we talk about the hydrogen carbonate ion, HCO3 minus. So it almost acts similar to the HSO4 minus. So look at something. So when this guy here acts as an acid, and then it also acts as a base, right? So when HCO3 minus acts as an acid, what actually happens? When it acts as an acid, it then forms, so remember, what is an acid? A proton donor. So when it acts as an acid, what happens? It gives away a proton and it forms CO3 2 minus, right? Similarly, when it acts as a base, what does it form? It forms H2CO3, right? So if you could think of a typical example of how this actually works. So let's say we have a certain example here, right? Let's say we're having a reaction of, let me see, HCO3 minus plus water. Now, are we expecting HC3O minus with water to react as a base or as an acid? It can be any. Remember, if it acts as an acid, then it's supposed to give a proton. But if it acts as a base, then it's supposed to accept a proton. If it acts as a base, then it accepts a proton, right? So what then do I have here? So I have HCO3 minus plus water. And what does that actually give me? Let's say it acts as a base. When it acts, let's say in this case, this is when it acts as a base. This is when HCO3 minus acts as a base, and then we'd have a reaction again here when it acts as an acid, right? So I'm just going to rewrite this. So it's HCO3 minus plus water. Okay, So when it acts as a base, what does it form? When it acts as a base, it forms this guy. So it acts as a base, and then it forms. Oh, just realized I might actually run out of space. Okay, never mind. We'll just do this. Wait, what? Okay, never mind. Just a problem. Okay, so when it acts as a base, what happens? So if you act as a base, what is it supposed to do? It's supposed to accept a proton. Therefore, we're going to have H2CO3, right? Why do I not have space? I think I'm just going to write this below. I'm just going to take everything and just write it just underneath. Okay, cool. So it forms H2CO3 plus a hydroxide ion, right? So think about it. It formed a hydroxide ion. According to the Arrhenius definition of a base, what is a base? Substance that forms hydroxide ions when dissolved in water, right? So in this particular case, it is safe to say that this is a reaction, reaction 1 and reaction 2. This is a reaction when HCO3 minus acts as a base. It receives a proton and it forms this guy and that guy right there, right? Which is basically what we said here. When it acts as a base, it gives you him. So what happens when it acts as an acid? Remember, when it acts as an acid, it's supposed to give away a proton. So what happens? It gives away a proton to water. What do we then have? CO3, 2 minus, plus a hydronium ion. Remember, definition of an Arrhenius acid, it is a substance that produces hydronium ions when dissolved in water. So in this case, when HCO3 minus acts as an acid, it forms this guy and the hydronium ion, which is exactly what we said here. Okay, just hope that you guys are all fine. If you have any questions, please do ask in the comment section and I will get back to you as quick as possible. Okay, now that we've gotten that out of the way, we could actually look at what we call the pH scale. The pH scale. Right. So we look at the pH scale. What exactly do we actually talk about when we talk about the pH scale? So when you talk about the pH scale, remember, we have acids as well as bases. So we have acids and we have bases. So the pH scale is a scale that basically tells you how acidic or basic, or maybe some might say alkalinic, a certain substance is, right? So if I say to you, we're talking about a pH scale, right? Like I said, it basically tells you how acidic or basic a certain substance is, right? So if you look at the pH scale, this is how it actually looks like. So on the pH scale, okay, I think we should start with the definition. It's not really important for the exams, right? But I'm actually not going to write it down. I'm just going to say it's not. We're not going to be asked about it either way. So by definition, a pH is a negative logarithm of the hydrogen ion. So it's something like this. It's not important for you guys at the moment. So it is the negative logarithm, right? We say it's the negative logarithm of the H plus ion, or you could actually just write it as negative log of the hydronium ion, right? Do not write this down. This is not important at this moment in this grade, right? So that's what it basically is. That's what we talk about when we talk about pH, not the scale, but the pH, right? So what exactly, or rather, how exactly does the pH scale look like? So a pH scale ranges from 0 all the way to 14, right? So I'd have my 0 here, and I would have my endpoint here, which is 14. And then obviously, in the middle, we would have 7. So with my pH scale, what what does it actually tell me? Now, I want you to note this. Anything below the pH, if you have a pH value, right? If you have a pH value that is less than 7, or some substance that has a pH less than 7, we say that that particular substance is acidic, right? So this section here is the acidic section, right? Remember, the pH is less than 7, so we say that particular section there is acidic, right? And then anything with a pH greater than 7 is known to be alkalinic. Alkalinic, or some might say basic. Basic just means it's a base, right? So this section from 7 going all the way to 14, we say that something is basic. Cool. Now, we've looked at the pH scale, and we've said that the pH scale basically says, so in essence, right, the greater, right, or rather the more, or rather the concentration, if you have a greater concentration of the H plus ions, if you have a greater concentration of the H plus ions, right, then that particular solution becomes more acidic, right? Remember, according to the Arrhenius definition of an acid, it's a substance that produces H plus ions. If a substance produces H plus ions, we say that something is an acid. So if you produce more and more and more and more and more and more of H plus, then that particular concentration of H plus increases and makes a substance way acidic, right? And the opposite is true. And obviously, if a substance is acidic, then it has a very low pH, a pH somewhat closer to 0, right? Cool. And then obviously, if a substance produces more a low concentration of H plus ions, then we say that particular substance, it produces a low concentration of hydroxide ions. We say that it is basic. It's a base, right? If it produces a low concentration of H plus ions in a solution, we say that it is alkalinic, or we say that it is basic, right? So now that we've looked at that, what do you think actually happens at 7, right? I mean, if when I get to number 14, I know that my particular substance is very basic, right? It's like a very, very strong base when it's at 14, right? So if it's at 14, it's a very strong base. What happens when we are at 7 exactly, right? Now think about it. If I am below 7, I am acidic. If I am above 7, I am basic. If I am at 7, that means I am both acidic and basic. We use a simple term and we say you are neutral. So you reach a point where your particular substance is neither basic nor acidic. It's just neutral, right? Say that at 7, a certain substance is neutral. At exactly 7, a certain substance is neutral. At 0, we say that something is very acidic. It's a strong acid, so very acidic. Very acidic, right? Acidic. And then at 14, we say that a substance is very basic. It's a base, right? And then at 7, what is it? It's neutral. It is neither an acid nor a base, right? And then obviously, if you say, let's just say you had a certain value here. Let's say this was 9. Obviously, whatever the substance you would have that has a pH equal to 9, then that particular substance is then obviously considered to be a base, right? But think about it. If you get so closer and closer and closer to 14, you become stronger and stronger and stronger of a base. But if you're a bit far from 14, above 7, just so far from 14, you are a base, but you are not a strong base. Rather, you are just a weak base, right? Same thing with the acid. If you are somewhere just around here, at this point here, let's say this was 5. If you're at 5, you're a bit distant from 0, but close to 7, still below 7. Therefore, you are still acidic, but you're not a strong acid. You are a weak acid, right? So that brings me to the different types of acids. So we have strong acids as well as strong and weak bases. Cool. So we look at strong and weak acids and strong and weak bases. So what is a strong acid? A strong acid, by definition, is an acid that that ionizes. I'm so sorry. So a strong acid is an acid that ionizes completely. It ionizes fully, right, or completely, right? So a strong acid is an acid that ionizes fully or completely. And obviously, a weak acid would be the opposite of that, right? It does not ionize fully, right? Then a strong base is a substance that dissociates. Oof, that's a very terrible handwriting. Ugh, horrendous. So a strong base is a substance that dissociates fully or completely, right? And then obviously, what would be a weak base? A weak base is a substance that does not dissociate fully. So we have different types of weak acids and different types of strong acids and different types of weak bases and strong bases, right? So if we look at our common strong acids and our common weak acids and our common strong bases and common weak bases. So if you look at our common acids, right? Our common acids, we would then have acids like, I think I should just indent this just a little. Yeah, right there. We will talk about HCl, nitric acid. Remember, this is hydrochloric acid. Hydrochloric acid. And this is nitric acid, right? And then we have sulfuric acid, H2SO4, or hydrogen sulfate. I'm just going to say hydrogen sulfate, or some may say sulfuric acid. Okay, cool. So we have our hydrogen sulfate, our nitric acid, and our hydrochloric acid. And just remembered another one, H2SO3, I'm assuming, and I think this is what we call hydrogen sulfide, yes, or sulfurous acid, yes, sulfurous acid. I have bad spelling, but anyway. Okay, so these are our common acids, but all of these acids I've listed here are regarded to be strong acids, right? Strong acids. So these are acids that we would actually expect to have a pH that lies just between 7 and 0. Right, so the pH of these would just lie between 7 and 0. But to be more precise, we would just say the pH just lies between 0 and probably 4. Just for more precision, because these are very strong acids. You would never, I think I'm just making a very bad restriction here. Just make it 5, just to be safe. So what I basically mean by these is that these are acids that are so strong that they have a very high concentration of H plus ions. There is a very high concentration of H plus ions in these mentioned acids, right? And then any acid not mentioned here, if I talk about different types of acids and I look at acids like acetic acid, acetic acid. You would find acetic acid in vinegar. Some may call it ethanoic acid. Really, I feel like there's more of a, I don't know actually, because apparently there's like a new like, it's, when as time goes, people just decide to not use a word anymore. So it's like, is it ethanoic acid or is it acetic acid, which scientists don't really use much anymore. They don't use it more often. They just decide, okay, let's just change it and just call it by acetic acid or call it by ethanoic acid. And it's a, it's a lot. It's quite a lot. But anyway, okay. So we're looking at acetic acid and we look at phosphoric acid. Remember, H3PO4. Phosphoric acid. Phosphoric acid, right? And we also look at hydrogen carbonate, H2CO3, or some may call it carbonic acid, dihydrogen carbonic acid. Okay, so these listed acids, right, are the acids that are considered to be, yes, you guessed it, weak acids, right? And you would expect the pH to still be just below 7, but maybe from 3, right? These are very low, weak acids. These are, okay, I mean, if I restricted that part there to be, okay, so it's just going to be from 0 to 7, right? But you would expect their value of the pH to be quite close to 7. Just so close. It gets closer and closer and closer to 7. Just somewhere. If 7 is here, then you find the pH is somewhere just here. That would be the pH for these particular substances. That is how weak they are. So in essence, when the pH of a certain substance is closer to 0, it's more acidic. But when it's closer to 7, it's still an acid, but it's less acidic. It's a very weak acid, right? And then what else do we look at? We look at weak acids and strong base. So we look at our common bases, right? Now we are looking at our common bases. So we'd have our first base, potassium hydroxide. Potassium, as the Americans would say it, potassium. Is it 2 T's? Ooh, I really suck at spelling. I'm assuming it's 2 T's. Potassium hydroxide. Potassium hydroxide, sodium hydroxide. This one should be fairly easy. Sodium hydroxide, as well as sodium hydrocarbonate, sodium hydrogen carbonate, NaHCO3, sodium hydrogen carbonate, sodium hydrogen carbonates. Okay, so these three are known as our strong bases. So we would have a pH, you would expect the pH to just lie between 7 and 14. Remember, the closer the pH of a substance is to 14, the stronger of a base it is. The closer it is to 7, it is a weak base. As long as it's above 7, but closer to 7, then it's a weak. Let's say it has a pH of 8 or a pH of 7.9. That's a weak acid. Sorry, a weak base, not an acid. Okay, so anything that's not this, so we're talking about substances like ammonia, right? So we look at substances like ammonia, we look at substances like sodium carbonate, sodium, terrible. I used to speak a little bit of Spanish. Wait, is it Spanish? Terrible. Yeah, I'm assuming it's Spanish. Okay, so it's CO3. So it's ammonia. sodium carbonate, sodium carbonate, as well as what's this other one? Calcium carbonate. Yes, calcium carbonates, calcium carbonate, calcium carbonate. Fun fact: the word carbonate is a Latin word. That's why I say carbonate. I'm kidding. It's actually not a Latin word. But anyway, okay. So we have then our weak bases, right? So we would expect these to have a pH just in between 14 and 7, but way closer to 7 than it is to 14. So let's say ammonia would have a pH of just a typical example, maybe a pH of 8.1. That's so far from 14, but quite close to 8. I mean to 7, right? Let's say calcium carbonate has maybe a 7.5 pH. These are our weak bases. Okay. Now we've looked at acids and bases. We've looked at conjugate acid-base pairs. We've looked at amphilites. We've looked at weak acids and strong acids, and we've looked at the pH scale. And I think right now that concludes the end of that just brings us to the end of this video. And then the next video, I will then look at the composition between weak acids and weak bases, concentrated and diluted acids and bases. What influence does the strength of an acid or base actually have? And then we're going to look at different types of reactions, acid-base reactions, right? But anyway, from me to you, I shall see you in the next video. Have a good day. Thank you. Bye-bye.